Alright, the last one that we're going to have a look at on this is DNA profiling. And so this is a real key concept that we talked about in the first topic, so not something I need to go into in too much depth. I guess just the rationale as to why we would not choose to use this is because it's probably a lot more time consuming and expensive as DNA hybridization or comparing amino acid sequences between organisms. So this is where we're going to use things like short tandem repeats and things like that, and the actual full profiling technique to be able to determine exactly the base sequences of organisms to determine how closely related they are. And so, get back into DNA profiling. We can see that, as we talked about in topic 1, short tandem repeats are unique to individuals. So what we can have a look at is to compare exactly how sequences are from one organism to another, or between the same type of organism. We can use those restriction enzymes. We can amplify using polymerase chain reaction. We can actually then allow those segments to move across, and if they are genetically exactly the same, they're going to move the same way along an electropherogram as well. So again, like I said, I'm not going to go into too much depth around PCR because PCR is something that, DNA profiling, including PCR, because it's something that you should be able to go back and watch previous videos on. So a phylogenetic tree, this is sort of something that seems relatively simple, but I guess it's really important that you understand the key terminology that we use to be able to classify organisms and to be able to create these phylogenetic trees. And so this whole tree is able to show us the inferred evolutionary relationship that exists between individuals or organisms based on similarities and differences in the genes and their physical features. And so when we have a look at that, what we can see is we can see terminals or taxas represent individual species. So they are points right at the end there. You can see then the nodes. So that blue one there between B and C is the last common ancestor that exists, or a single species that was before it diverged into species B and species C that are now distinctly different, that cannot actually reproduce in the same way that humans can with each other. So that might be humans and monkeys, but they share a common node, which is an evolutionary ancestor. And then sister or taxa species, so that's when we're starting to look at species that diverge from the same node. Like I said, the ones there, B and C, we would consider them to be sister or taxa species, the same as E and F, the same as G and H, whereas we probably wouldn't say that about D compared to H, because then we've got all these other things that happen in between there. It would be D compared to whatever that pink one is. That would be a sister taxa species for those. Alright, and so we can draw conclusions from that. So we can see here that we've got things like you can identify common ancestors. So we've got this point here where we can identify this node and that common ancestor between A and B. So that was when one species became two distinct ones. We can then look at common ancestors that exist between different completely different species now as well, and we can see that the root cause, if we go all the way back, this is the early organism before it actually started to evolve into distinctly different things. We can see here that there was one point where E and then what would become A, B, C and D became completely different. So if we said that this here was F at this point here, we would say that E and F would be sister taxa with each other. We would say C and D would be sister with each other, and then A and B